A very good day to all. Welcome back to Chapter 2B on the simulation of heat exchanger. In the previous session, you have been briefed about the model available in X1 Plus to allow you for the simulation of heat exchanger. So the simple model would be heater, and you have another model which is a more complicated model to enable a rigorous simulation on heat exchanger, which is heat X, right? And you have also tried exercise 2.3, which is a simulation of heat exchanger using heater, a simple model. So now let's move on to exercise 2.4 that you need to actually simulate the same process as in exercise 2.3 using the model of heat X, right? Let's look at the question. So this is the question for exercise 2.4. So again, the case is the same with the one in exercise 2.3. So we have this fuel 12 at a feed flow rate of 10,560 kilogram per hour that needs to be heated from 240 Kelvin to 300 Kelvin. And ethylene glycol here, which is fed at 350 Kelvin at the shell side, will be used as a hot stream to heat up the fuel 12. Right. So a typical core current shell and tube heat exchanger will be used, and the plant manager recommends that the minimum temperature approach should be at least 10 Kelvin, and he also recommends that the tubing should be using 20 British wall gauge carbon steel tubing with a pressure drop of at least 0.67 for either the shell and the tube side. So now your task is you have to simulate the heat exchanger process using heat X model and determine the heat duty required and heat transfer area. So let's analyze the problem before we start solving the problem. So the purpose of this heat exchange process is to heat up fuel 12 from 240 Kelvin to 300 Kelvin. So you must know what is the objective of your heat exchanger. And hot stream here is ethylene glycol, and cold stream here is fuel 12. Okay. The property method recommended here is NRTL-RK. The NRTL for the property of liquid and RK for the property of vapor, which is not more than 10 atm. So the model used must be heat X as stated in the question. So two feeds specification are required, hot stream and cold stream. In this case is you have hot stream, ethylene glycol, and the cold stream is from 12. And remember, the minimum temperature approach must be at least 10 Kelvin. So this information also must be included during the simulation. And the type of heat exchanger here is shell and tube core current heat exchanger. Okay. And the specification for the stream is also summarized in the diagram on your right. Okay, this is the diagram. Now, before we start solving the question, you must able to understand what is the meaning of minimum temperature approach. Then only you can solve the problem accordingly. Okay. So we have two cases over here. So the case at the top is actually for a temperature profile of a core current heat exchanger, right? And you must have learned this in your heat transfer subject. So if it's a core current heat exchanger, the minimum temperature approach here is the differences, or it is the temperature difference in between the outlet temperature of your hot stream and also the outlet temperature of your cold stream. It must be at least 10 Kelvin to ensure an effective heat transfer. Right? So in this case, especially in exercise 2.4, the cold stream information is fixed, including the flow rate. So we can't do much changes on this because 300 Kelvin as the outlet temperature of the cold stream is also over target. So what is the variable over here is the hot stream variable. So we can always adjust the hot stream specification to ensure the minimum temperature approach of minimum 10 Kelvin. So the case at the bottom is actually for the counter current heat exchanger, and this is the temperature profile for the counter current heat exchanger. So the minimum temperature approach here is referring to the temperature difference in between the outlet temperature of the hot stream and the inlet temperature of the cold stream, okay, for counter current heat exchanger. So in this case, if you want to keep a minimum temperature approach of 10 Kelvin, so we can always adjust the variable or specification of hot stream to ensure the outlet temperature of the hot stream is at least 250 Kelvin and above. Okay, so this is for counter current. But in our case, we are having core current, so we have to ensure the outlet temperature of the hot stream here is always more than 310 Kelvin. Then only we can fulfill the requirement on the minimum temperature approach. Right. Let's move on to solve the problem. So as usual, you have to first list down all the chemical components, and then you have to select the property method under the property tab, and after that you have to shift to the simulation environment. So this is a simulation environment here. So you have to shift here and start constructing the flow sheet, right? And when you construct the flow sheet, you have to select the correct model, the process model, and also you have to include the required stream to the model. Okay. Now, remember you have to use heat X. So under heat X, you can go to you see under this. Under the heat exchanger, you can have a heater, heat X, and some other model for the simulation of heat exchanger. But in this case, it's heat X. Just click on it, and you have a lot of options here. Okay. In our case, remember the hot stream must be in the shell side. Okay. There are two possible options here. Okay, which is if you refer to the the box over here, refer to the first row, so it's the third box and the fifth box. So if you refer to the statement came out when you put your cursor here, it is basically for you will actually stated HT, meaning hot stream is in the tube. So HT means the hot stream is in the tube. So this is for the third box, okay, the icon in the third box. While the icon in the fifth box will be stated HS, meaning hot stream is in the shell, which match with our case, right? The ethylene glycol in exercise 2.4 passes through the shell side. So we have to choose this HS, the icon in the fifth box, as your process model. So once you have chosen the process model, of course you have to include the required stream. So in this case, hot stream and also cold streams are required. Okay, when you put your cursor here, actually you can see there is an instruction saying that this is for the hot stream inlet. So you just put one stream here, inlet, and hot stream outlet, and cold stream inlet, as well as the cold stream outlet. Okay. And for sure, you have to recognize which one is actually the tube section and also the shell section. So the tube section here, if you refer to the line, the black color line here, the horizontal line, that is actually the tube section, which is for the cold stream. While the shell side is actually the gray shaded section, and our hot stream must pass through the shell side based on the details of the question given. Okay, now once you have put in the process model and you have insert the required stream, then it's time for us to include the specification for the stream. Okay. So first we work on cold stream. So we have to put in the temperature and pressure and also the flow rate, and all these are given in the question. Okay. Remember, you have to remember the feed flow rate here is actually given in terms of mass. So it is 10,560 kilogram per hour, and the mass fraction is 100% to freon 12, right? Because we have only freon 12 as a cold stream. So the mass fraction is 1. Okay? Fraction must be maximum is 1 because it's a fraction. And you have to put all these detail in the cold stream. The cold stream spec. Okay. So this is the cold stream spec. And so let's continue. So once we have the specification for the cold stream, then we are now in the page for you to include the specification for the hot stream. So if you don't know which page to go, you can always click next. Okay, once you click next, it will be guided to the next step if you don't know what is the next step, right? But if you are familiar with the software later on, normally you can do it on your own because you know what will be the next step, right? But if you don't know, no problem, just click next, then you'll be guided to the correct step. So now for hot stream, you have to put in the temperature and pressure as given in the question, but in the question you are not given the flow rate. So in this case, I'm putting an arbitrary flow rate, say 95 kilomole per hour. So I have put in ethylene glycol as 95, and the unit here is flow rate kilomole per hour. Okay, these are the specification for the hot stream. And the next thing is we have to put in the specification of the process model, and we are having heat X here. So for heat X, so we are still sticking with this shortcut method, okay, shortcut. And here we have to choose core current based on the information given in the question, and we have to specify also our target here. Our target is we would like to heat up the cold stream from 240 Kelvin to 300 Kelvin, meaning the objective over here is to have the outlet temperature of the cold stream as 300 Kelvin, and the minimum temperature approach is 10 Kelvin. Just set this accordingly. Alright. Okay, moving on. If you go to the next page, just now we are actually in this specification page for the process model or for the heat X model. And if you move on to pressure drop, you're supposed to include either the shell or tube section for a pressure drop of 0.67 atm. So in this case, I have actually chosen hot side. So I put hot side, and the pressure drop is 0.67 atm. Minus here to indicate it is pressure drop. So if you put positive 0.67, that is the pressure in the tube, not pressure drop. So if you want to indicate pressure drop, you must put minus, okay? And that is why it is minus 0.67 atm for the hot side. Okay, remember, for the hot side. Okay, now we have actually completed all the required information, and you will click next. It will be guided to a page asking you whether you want to proceed the simulation or not. Okay, just proceed the simulation, run the simulation, and you get all these messages pop up. So let's look at this message. What is this message all about? Okay, it's saying that there are errors, and this is because of the temperature crossover detected. So meaning to say, we may not achieve the targeted minimum temperature approach, and that is why your hot stream temperature profile is crossing over with your cold stream temperature profile, like this one. So if this is not met, this requirement is not met on the minimum temperature approach, so these two lines will be intersecting, meaning there's a temperature crossover, right? And the error is because of this. Okay. What should we do to get rid of the error? As I mentioned earlier, we cannot do anything on the cold stream. We cannot adjust the cold stream, but we can adjust the specification for the hot stream. So in this case, we can adjust the flow rate of the hot stream in order to ensure the minimum temperature approach, right? Okay, now let's change the ethylene glycol flow rate, which is the hot stream flow rate, from, I think earlier on we said 95 kilomole per hour. Now you set it to 120 kilomole per hour and run the simulation again. Okay, once you run the simulation again, you see now the status is clear. It is results available without error. Okay, and if you check the temperature for each stream, the inlet outlet temperature for hot stream and the inlet outlet temperature for cold stream, okay, and you can see the minimum temperature approach is actually achieved, right? You see, we need at least the outlet temperature for the hot stream must be at least 310 to ensure the minimum temperature approach of 10 Kelvin. So now we are having 316. So this is more than enough to give you a minimum temperature approach of 10 Kelvin. Okay. So we have done on the minimum temperature approach, and the results are also available without error, meaning now all the results available in the simulation is reliable. Then we can start checking the answer that we need to support the question. We have to first identify or determine the heat duty required and also the heat transfer area required. So if you go to the navigator, this is the navigation tab. So go to the model section under thermal result. You see thermal result. You can actually check the heat duty required. Okay, in this case it's about, I think it's about 40,000 calorie per second, and the required exchanger area is about 4 meter square. So these are the answer that you have to include to the question in order to answer it accordingly. So moving on, you have some tasks, some additional tasks for you to enhance your understanding on the simulation of heat exchanger using HeatX. So now you have to adopt the, of course you can adopt the sensitivity analysis option to carry out the task, or you can also vary the EG flow rate manually one by one and try to get the outlet temperature of the hot stream and put into the table, right? And of course, after you construct the table with result, you have to conclude the findings, okay? And repeat the simulation. If you look at the second point here, so repeat the simulation for the same heat transfer process in exercise 2.4 using a counter current heat exchanger. Determine the flow rate of EG that could keep the minimum temperature approach of 10 Kelvin. So now instead of core current heat exchanger, you have to use counter current heat exchanger and see what are the changes in terms of the flow rate of EG in order to give you the minimum temperature approach of 10 Kelvin. Do we need a higher flow rate or lower flow rate? Of course, it depends on the heat transfer efficiency of a particular type of heat exchanger. Which one is more effective? Probably you can guess based on your knowledge in heat transfer. Right. So I think that's all for exercise 2.4. So remember, try the additional question given to you to enhance your understanding. So I will see you in the next session. Thank you so much.